Hello and welcome everyone to our talk. Thank you for being here. Sorry for the late start. But yeah, so unleashing Flutter on embedded hardware with the help of flutter-pi. Okay, so first off, who are we? Basically, the three of us, Werner, Hannes, and me. And we work at a company called KDAB. Basically, we've been doing software for the past 20 years with Qt and C++, and we're experimenting with Flutter more recently, which brings me to our initiative called Industrial Flutter. Basically, we explore Flutter for industrial use cases. We have a website with some blogs, a YouTube channel, and also a Discord channel. So you guys can join there if you'd like to. Okay, so before I go any further, I just want to make sure we're all on the same page. How many of you know what a embedded device is by raise of hands? Okay, this is a pretty well-informed audience so far. So basically, as you all would know, it's a specialized device that is used for specific tasks or functions. And typically, we have limited processing power and memory available on these embedded devices. Okay, so the company we work for has done lots of work for customers in the past in the embedded industry. So let me show you some examples. The first one is for beer brewing machines. You can see a touchscreen there. By the way, this isn't done with Flutter. So it's got a touchscreen, shows some temperature, regular embedded device. Then there's also electric scooters. There you can see, it shows the battery, some navigation, basic stuff. Also laboratory machines. And then this one, believe it or not, was actually done using Flutter. It's a smart tennis court. Uses flutter-pi under the hood as well. And then get ready for a big jump. There's also another example of an embedded device. It's a spaceship control interface. Now, how many of you have been to our booth today or yesterday and saw the spaceship control interface? By show of hands. Okay, if you haven't tried it, please come try it afterwards or tomorrow. By the way, it's for a super secret client in the space travel industry, but the details are confidential. Okay, so this hardware that we have here is not powered by Raspberry Pi, but rather by let me put up the next slide. It's a single board computer manufactured by a company called Toradex. So on this single board computer, we have a system on module, or SOM as we call it. And the system on module houses the CPU, GPU, and memory. And the carrier board there is it's similar to the motherboard of a computer. So let's zoom in a little. So on this specific SOM, we have a SoC, or a system on chip, which is called the AM6254, along with 2 gigabytes of RAM. Now, we're nearing the end of the rabbit hole. On this specific SoC, we have 4 ARM Cortex A53 ARM cores and an entry-level PowerVR GPU. Now, let me translate this to mobile developer terms. Basically, this is a potato that we're using here. It's roughly equivalent to a entry-level smartphone from 5 years ago. Snapdragon 215 kind of vibes. So in the embedded industry, this is considered pretty decent mid-range hardware. Now, some of you might wonder, why exactly is this? So imagine you are creating a medical heart rate monitor for hospital use. Would you pick the latest and greatest brand new SoC, or would you rather consider things like price, whether the SoC has a proven track record or not, whether the architecture of the processor is considered reliable? Also, will you be able to buy this SoC in 5 years' time, 10 years' time, that kind of thing? Also, what's the life cycle of your product? How long does it need to last? 3 years, 5 years? Get the idea. By the way, the manufacturer of this specific system on module that we're using, they plan to start volume production this year. And according to their roadmap, they will be manufacturing it up until 2033. So yeah, we'll still be stuck with ARM A53 core devices in a few years' time. But it gets worse even, actually. Like on the website of this particular like embedded hardware manufacturer, they also say that they are manufacturing a single core ARM A7 processor with a 512 megabytes of RAM and a graphics controller. I mean, you can't really call it a GPU. And they plan to be manufacturing this up until 2036. So yeah, this is quite different from the mobile industry, where we're used to much more powerful hardware. Okay, so resources are very limited. I think I made that quite clear, which is where a wonderful piece of software comes in. It's called flutter-pi. Yeah, so what on earth is flutter-pi? Let me explain. Flutter-pi is a lightweight Flutter engine embedder for Linux embedded, and it runs without X11 or Wayland. Now, some of you might be wondering, what is a embedder? Now, to answer that, we quickly have to take a look at the Flutter architecture. Now, the Flutter architecture consists of 3 main parts. There's the framework, the engine, and the embedder. Now, if Flutter were a car, basically, the framework would be like the interior of the car. Like you have the gear stick, the steering wheel, and the pedals. In the case of Flutter, this is like the regular stuff you deal with on a daily basis. Material, library, Cupertino library, painting, animation, all that stuff. The engine, that's kind of like the engine of a car. It's like kind of complicated, and you want to keep the hood of the car shut, mostly not deal with it. But yeah, except for a few people that enjoy paint, they like working on these kinds of things. But luckily, the Flutter team does most of this for us. And then right at the bottom, we get the embedder. Now, the embedder is like the drivetrain of the car, or let's say the wheels rather. This is because it connects Flutter to the platform that it is running on, the same way the wheels of a car connects it to the road or the surface that it is driving on. Okay, so the Flutter team provides us with a few different Flutter embedders out of the box. There's one for Android, iOS, macOS, Windows, Linux, I think one for web as well. Which brings me to my next point, Linux. So in the embedded industry, Linux is very popular. I think the fact that it is open source, reliable, and free to use plays a big role in that. But yeah, enough said. So all we can do is, as I mentioned earlier, take the desktop Linux embedder, run Ubuntu on our hardware, and we're done, right? But hold on, not so fast. This is what it looks like when you run Flutter on a desktop Linux distribution. So you have the embedder, then you have GTK as a dependency. There's also, like, you can either use X or Wayland, and then only then you get to the Linux kernel, and then eventually the hardware. yeah, so this is a bit of a big stack to be running on such limited hardware, which is why we prefer to use Flutter-pi. Now, Flutter-pi allows you to directly run your Flutter app, but more on that later. Yeah, there's also other third-party embedders available. There's one from Toyota called IVI Home Screen, also one from Sony. But yeah, now I'm going to hand over to Flutter. Hannes, he's the author of Flutter-pi. Yeah.
Okay, everyone. So let me start with the question. Who here has used Flutter-pi before with the Raspberry Pi, for example? Okay, quite a lot of people. Then this might not be completely new to you. So first, as Pieter has mentioned already, Flutter-pi is the so-called Flutter engine embedder. And there are many embedders out there. And in this workshop, we're going to be talking about Flutter-pi mainly. So Flutter-pi is about 30,000 source lines of code of C code. It can run using OpenGL ES or Vulkan. Originally, it was meant for the Raspberry Pi, that's where the name comes from, but it also supports other platforms now. You can run it on an AMX. We actually had a project with Texas Instruments where we made it work on their new hardware platform and generally optimized the Flutter performance on there. You can also use Rockchip boards if you want to. Okay, but let's look a bit closer at what jobs the embedder really has. And this part is going to be a bit technical, but I promise it will get better afterwards. So the engine does most of the heavy lifting for a Flutter app. And the platform-specific parts are left to the embedder. And one of these tasks is providing the engine with an OpenGL ES or Vulkan rendering surface, initializing the graphics API in general. And because the engine can speak both OpenGL ES and Vulkan, and for example, by default, it doesn't know which one it should use. So the embedder needs to tell that to the engine. It also doesn't know where the engine should render into. So you need to configure that for the engine. And then for the Flutter-pi case, for example, we need to tell the engine to render into a surface that can be directly scanned out using the Linux kernel. And the embedder also has the job of providing a plugin API. So that's not provided by the engine itself, but by the embedder. And also implements some core plugins like text input, the mouse cursor, which icon should be used, and the system navigator, app lifecycle. Also provides the engine or Flutter app with the user input. Yeah.
Good question. How long has it taken you to write this embedder?
I mean, I'm working on it in general since 5 years now, but I think the first picture took maybe a month because all these APIs are really undocumented and it's really hard to get information about it. And
it's still quite a short time. So still quite a short time. So you've been working on this for 5 years, yes, already.
Yeah, 2019, yeah.
Nice.
Yeah, thanks. And also implements the event loop. So you might know Flutter uses multiple threads, one for writing the commands for the graphics API, or encoding the commands for the graphics API, and one for handling one that the plugins run on, and the embedder has the job of handling the events for these multiple threads, and also does app packaging, so loading the Flutter engine and the app. So to get a bit of a grasp of how that's done in detail, let's have a look at the Flutter-pi architecture. And so on top of there, you can see Flutter-pi, and above there would be even the engine and the Flutter app. And for graphics, Flutter-pi normally talks to the normal Linux graphics driver stack. So GBM for allocating the graphics buffers, EGL for managing GLES basically. And that's similar in the Vulkan case, except we of course use Vulkan there. And once Flutter has rendered into these buffers, Flutter-pi presents them on the display using an API called KMS, which is the Linux kernel interface for display output. So there's no indirection between it, and the touch input first comes of course from the Linux kernel, and then it goes to something called libinput, which is used by all major Wayland compositors too. And so yeah, that just makes it a bit easier to use input from the kernel directly, and also handle some device quirks, stuff like that. And the event loop is provided by libsystemd, and the key to text mapping is done by something called libxkb common. Okay, so something else, the Flutter SDK only supports official platforms, and mostly, and I say mostly because there's a feature called custom devices, which I'm going to use later to do the practical part. And we've contributed that to some time ago to the Flutter SDK, but it's really incomplete, doesn't work that well. It's a bit buggy, I would say. And to get a better experience with Flutter-pi, there's a custom tool called Flutter-pi tool, and it works on Windows, all major operating systems, and works with most Linux targets. So you can do cool stuff like hot reload, DevTools, all that works with completely custom platforms like a Raspberry Pi. And one thing that's missing right now is VS Code integration, but that will come in the future. There's also some other tooling from Snap Embedded, and they also had their own talk as well, it was yesterday. And they use a kind of different approach, but it also works pretty well, and they support Flutter-pi there as well. And yeah. Okay, one other thing that is really hidden to most users is the Flutter engine binaries. So you've probably seen them when updating your Flutter SDK. Yeah, this screenshot there, that's the process of downloading the pre-built Flutter engine binaries that come from some Google infrastructure server. And that's a good part of your finished Flutter app is actually the Flutter engine. And for embedded or for custom embedders, we unfortunately can't really make use of that. Because for the official platform, it's built by the official Flutter CI and stored on the server. But for custom embedders, we need to specify some special build flags to the engine. And so I have my own Flutter engine CI. Sony does too, by the way. They also have their own embedder. And that just watches the Flutter repository for updates and then builds the engine if necessary. And who here has built the engine before or worked with the engine directly before? Okay. Yeah, well, it's quite a big project. So when you compile it, it's like 5,000 to 7,000 C++ files. So it's pretty huge. You can't build it on a slow PC. It takes forever. So I made it fit entirely in the GitHub free tier. So I don't pay anything to build it. And yeah, that's good. It's also good for my pocket because otherwise I'd probably have to spend a lot on infra builds. And I had to apply some tricks to make it work. For example, manually shallowifying all the Git repos that it uses, and removing some unnecessary parts of the checkout. Then it barely fits. But that's how the build pipeline looks like. It's, I think, 50 machines, maybe even more, running for 1.5 hours with GitHub free tier. But yeah, it works. And there's also some other reasons we use a custom CI. We need to specify some special patches to make 32-bit Linux ARM work because it's not officially supported. Also to allow cross-compiling the Dart compiler. So we can, for example, have a Dart compiler that runs on Linux ARM64, builds for 32-bit ARM, and was built on x64. So yeah, also to allow building this specific Dart compiler we need for macOS and Windows in general, because it also doesn't work by default. And yeah, that's all necessary so Flutter-pi tool can run everywhere. Okay, Pieter.
Okay, so now we are going to go ahead and, well, set up Flutter-pi with custom devices. As you can see, we already have a Raspberry Pi here. No, actually, like, not today, we're not really going to set it up since it's already set up. But if you guys want to go have a look, we have a YouTube channel and there is instructional videos there for setting up. I think the one there, connecting to a embedded device using the Flutter SDK. That's the one that will show you how to connect. Okay, so now we're going to do a code lab with the Raspberry Pi, which is where Werner comes in. Yeah. Screen. Yeah.
Yeah, just a moment.
That's a good plan.
Do you need the touch screen? I have to invite you to for the Raspberry Pi directly to the monitor.
Well, we kind of want to show the breadboard as well. So cool. Is that text big enough? Is the text visible, or do I need to make it bigger? Is it good? Cool. So yeah, let's get started. So first off, we are going to be controlling LED with GPIO. GPIO stands for General Purpose Input Output. And then we're also going to use it to detect a button press. And after that, we will dim or try to dim an LED with PWM. And then we will just be reading a real-time clock chip with I2C. So this is just a basic examples of what you could use Flutter-pi and for on a Pi. And yeah, maybe you guys can create something cool at home.
Is it working?
Yeah.
Oh, okay. So by show of hands, who of you here know what GPIO is? Okay, so pretty well educated audience. Yeah, so then I'm not going to go ahead and explain it. It's general purpose input output. And yeah, cool.
Okay, so first off, the Raspberry Pi has a header on it. It's basically the GPIO header, and it has a bunch of GPIO pins, some of which can do other things as well, which we'll get to later. But for now, we're going to just turn an LED on and off. As you can see in the wiring diagram I did, we have an LED connected to GPIO pin 23, which goes through a resistor to ground. And yeah, cool. So for this, I'm going to be using Flutter GPIOD, authored by Hannes over there. So if something doesn't work, we can blame him. Also, I was very rushed doing the wiring, so if it doesn't work, we'll just have Pieter have a look at the wires, make sure it's connected correctly. Cool. So first off, Flutter GPIOD allows you to list all the GPIO chips on the board. Sometimes there's more than one. And it also lists the GPIO pins or lines. So if you do this at home, you can use this piece of code to basically just identify the correct chip and GPIO pin. So I've done this already, but this is what the output should look like. The first chip is called GPIO chip 0, and it contains the pin GPIO 23. So basically, I'm just going to create two constant variables, so we can identify, like with the names, so we can identify these, the chip and the line in code. Yeah, basically, okay. Next, I just have some variables I'm going to create in the stateful widget. That's called the GPIO chip, just a reference to that. And oh yeah, you need to add the library to your application with pub.dev. So it's Flutter GPIOD. I've already done that, but you can just add it to your pubspec.yaml. And then next we need to actually assign these variables. So Flutter GPIOD gives you, you can create an instance and get all the chips that are on the device. So basically what I'm going to do is I'm just going to loop through them and find the one with the correct name. And then I'm going to do the same thing for the lines or the pins to find the correct one. So I'm just going to use the chip that we found and just basically find the line from there. We'll be doing this in the init state. Cool. So next up, we actually need to request ownership of this GPIO line or pin. This is a necessity on Linux. This is mainly just to prevent apps from like clashing and doing stuff on the same GPIO pin. Yeah, we'll be using the pin 23 as an output because we want to turn an LED on and off. So we'll be using the request output method provided by Flutter GPIOD. Cool, so let's maybe give this a try. Oh, hold on. We need to actually release ownership of the line, of the GPIO line, otherwise we won't be able to use it again. So that's important. Cool, so let's maybe give it a try. I'll just set the initial value to true, which should, in theory, turn the LED on if I start the app.
It's this LED here that you're looking at, by the way.
Ah, rub. Sorry, I'm very stressed. Cool. Now let's hope it works.
Maybe we can play some music while we wait.
Elevator music. Okay. Yeah. Yeah, let's let it run. Okay. Yeah, so this happens sometimes.
Looks like an error, but it's not really an error.
Yeah.
It's just
It's just a warning. Yeah, elevator music. Anyone play some elevator music maybe.
Guys at the back, can you?
Yeah, so sometimes these things take a while and you just sit around and wait, basically. Live demos, yeah. Yeah, I just did it just before it started, yeah.
What's the future plan for projects?
More demos, probably. More demos.
I mean, there's people using it in cars. There's Toyota using it in their cars. There's other car companies also. Like some hours ago, we had a company that produces exercise devices for top football teams that use Flutter-pi actually and Flutter on their embedded device. So, yeah.
Did that work?
Yeah.
Yeah. Cool. Yeah, so I'm just copying over the files. I see. I'm not down.
Oh man.
Oh man.
Yeah, it says API rate limit exceeded.
Yeah. That's because
Oh, this was a yeah.
because it was built completely. So yeah, the build is currently not doing everything.
Guys, is this an infrastructure issue?
Yeah, this has never happened before. We were running it before the live demo, like 5 minutes ago.
You want to modify the Flutter-pi tool quickly.
Can build it manually. Build bundle.
Yeah, we just. See if it works.
Looks promising.
Guys, this is what embedded development usually looks like.
Cool. Yeah, so it seems like we have the LED running at least. Okay, let me just add one more thing here.
Careful.
That only works with the one command. Yeah, after.
Yeah, okay, so I guess the next step would be to try to put a switch on the UI. So let me see if I can get that to work. So I'll just add a little bit of state, Boolean, to keep track of what state the LED is in. And a switchless tile. So one other thing that I noticed is we're going to use a workaround. So we're not going to request ownership in the init state and release it in the dispose method. We are just going to use like a workaround where we request it as an output and release it immediately after. This is because of some issues with hot restarting. So just for this demo or this code lab, I'm going to use this instead of the normal method. Yeah, by the way, this is going to be a blog on our website. So yeah, just to let you guys know. Cool, let's see if we can get this thing to run again. But first, I need to SSH into the Pi to kill the app that's currently running.
Yep, it seems dead.
Okay, cool. Let's just rerun those commands again. Not really, no, okay. Cool, so let's see if this will actually run with a button. Yeah, elevator music again.
Okay, it seems we have a switch here. Does it work? Is it on? Yeah. No, it stays on.
Ah, I think I know what it is. I forgot to in the init state. Yeah, I need to remove this. And also this probably. Hey, this time it actually, oh, that's nice. No error. Thanks, closed. I see you on my phone. Maybe. Cool. Yeah.
Okay, let's check if it works now. Ah, okay. Oh, there we go.
Cool. So next up, we're going to try and see if we can get the physical button to turn on the LED and turn it off. So this is the wiring diagram for the button. We have it connected to 3.3 volts and then the button and then the GPIO pin 24.
Okay, so I just want to make sure I understand correctly. Like, if that button closes, will we be able to detect the 3.3 volts at the GPIO number 24?
Yes, basically.
And then when it's open, it would be 0 volts, right?
Yes.
Okay.
Okay. So again, just some copy and paste work to do. Specifying the identifier for the button. Adding a variable so we can actually access it. And assigning the correct GPIO line to that variable. So yeah, Flutter GPID has a request input method, which basically adds a listener to the GPIO pin, and when it detects like a signal edge that's rising or falling, it will create an event that we can listen to on a stream. Now, signal edge rising means that the voltage on the pin goes from low to high, and vice versa for falling. Cool, so let me just add that to the application. And also I want to add signal edge stop falling. Cool. So we've requested input. We want to release it just out of principle. So for listening to the events, we have an on-event stream. So I'll be using that. So basically all this is going to do is going to print any events that occur when we detect when Pieter presses the button. So let's see, maybe we can build this and have it run the first time, hopefully. Nope.
Okay, so do I press the button now?
Yeah, try and press it.
Okay.
No dice.
Seems to be broken again.
Yeah, maybe a wiring issue. Oh, was there actually something? Yeah, actually, right.
Okay, let's test this.
Ooh.
Okay, guys, so it seems I have to hotwire it. Like the button seems to be broken, but maybe. Ah, okay, now it's working.
Cool. So yeah, we can see all the events being streamed to us. So I guess next step is to just add some logic to the event that will turn the LED on when the button's depressed and turn it off again when it's released. Did I spell this? Oh, great. Maybe. Let's try. It's funny how things never work on stage, but cool. Seems to be working this time.
Okay, so I press the button now.
Yes.
Okay, cool. Okay, cool. And the UI is updating as well? Awesome. Okay, can we get another clap?
Cool. So next we're going to attempt to dim the LED using PWM. Pieter, want to maybe explain what that is?
Guys, so how many of you know what PWM is? Okay, a little bit less than just now. So PWM, basically, all we do is we take a regular GPIO pin and we turn it on and off very quickly. This is to kind of emulate a lower power signal than it would be if it's on all the time. Do you have a diagram to? Okay, cool. Yeah, so basically there's the period and then there is the duty cycle. So the period is like how long or what the period of the square wave is. This is usually very short. And then the duty cycle just determines for how long the pin would be on. And for the rest of the time, it's off. But yeah, we'll see that in action just now.
Yeah, so for this, you actually need to do some setup on the Pi. I've already done this, but it will all be in the instructions on how to get that set up. So this is the wiring schematic. We have it connected to GPIO pin 2018 and ground. So I'll be using dot periphery for this step because they actually have a PWM. They basically have it set up for you to easily use PWM. It also dot periphery makes use of a C library called C periphery. I've also installed that on the device. And you can do it yourselves, or there are pre-compiled libraries that you can just copy over as well. Yeah, and I'll just be pointing dot periphery to this library using the set custom library function. So I'll just go ahead and do that. Next up, we have a pin, a chip number, and a channel number. In the process of setting it up, you should be able to find out what these numbers are, or if they are different. Most Pis, it should be the same. Just initialize this. Cool, so just creating an instance of the PWM class provided by dot periphery. Next up, we're going to just define the period and the duty cycle. So the period will be 0.01 seconds, which is like 10 milliseconds, I think. And the duty cycle will be 5%. And then we can just use dot periphery to set the period and the duty cycle. And of course, dispose of it afterwards. So for time's sake, I'm just going to immediately add the list tile with the slider. So Pieter can adjust the brightness of the LED from the UI. Cool. Let's see if we can get it working.
Guys, if you ever wondered why embedded engineers have a lot of free time, now you know. Exactly.
Cool. It seems to be running.
Okay. So now to see, I think it might be wired incorrectly.
Brown
The
brown one.
is it to what GPIO pin is it connected again?
18.
Number 18.
Yeah, the brown one.
So let's see if this still not.
There's also a switch. But it shouldn't affect
No. Just
Rewire it to GPIO.
you need to put the cable in the same row as the pin of the LED. In the other white, not white vertical, for example. Yeah.
This brown one. Oh,
No, the blue one is.
On the upper leg of the brown one is the one, and the blue one on the other.
I think the blue one is for the GPI regular GPIO demo, and then the brown one is for the PWM pin. And they are different. It seems we found the problem. Yes, they are shorted. Yeah. Let's see. There we go.
Cool. So the last thing. A break. You guys want a break or? Yeah. Okay, 5-minute break. Or do you guys want to continue? Like show of hands, who wants a break? Okay.
Yeah.
15. Okay. 5.
50 minutes.
Yeah. Okay, so no break.
Yeah. No.
Okay, this. Okay. Yeah, so next up, we're going to just read I2C, real-time clock using I2C. Pieter, maybe you want to explain I2C?
Okay, well, I guess I can do that. So I2C, or IIC, or I2C, whatever you want to call it. Basically, like you have two lines. The one is for data, and the other one is a clock line. And then you communicate with devices on on this bus. Basically, in this picture here, we have 3 slave devices and 1 controller or master device. But yeah, you can read all you want about I2C on Wikipedia or watch some YouTube videos about it. We won't be getting into the details of it today, but it's basically communication protocol.
Yeah. Okay. So you also need to do some setup on the Pi to enable I2C. I've already done that, but there are some nice tutorials on the internet on how to do that as well, and in the document. Cool. So this is the wiring diagram. So we just have a tiny RTC module connected to GPIO pin 3 and 2, and then to power. Yeah, okay. Let me actually explain this. So on a Pi, there's usually maybe one or two of these I2C adapters. You can list them using I2C detect-L by running this on the Pi. And at the moment, there seems to only be one of these. Sometimes when you connect things, more I2C devices, more chips will show up. But in this case, we're going to be using chip 1 or adapter 1. So we can use I2C detect-Y1 to actually list the devices or the addresses on the chip. Unfortunately, it seems that the device, the I2C chip, the ITC module is not showing up. As you can see, there's no addresses being detected. So that's maybe something we need to check before we continue.
Okay, so what might the problem be? Oh, I see the problem. Guys, maybe I can show you the problem. I think you should, like, okay, wait. No, it's the one wire was pulled, yeah, it's out all the way. Okay, let's see.
Nope.
Still nothing.
Nothing. Maybe switch the clock and data wires.
Okay. I mean, let's try that.
So what we are expecting is two of these addresses to be populated. Address 68 and 50.
Okay, is it working now?
No.
Okay. Ah, okay. Oh. Okay, give it a try.
Yeah, cool.
It's working.
Yes. Okay, so in this case, using dot periphery with I2C, there's not a library or a implementation for communication with a DS1307 chip that's on the RTC module. Not in Dart anyways. There are some other libraries. There's one, a C++ library that allows you to do that, to communicate with it. And then there's probably also a Linux kernel driver for communicating with it. But in this case, it was simple enough to just create a small Dart implementation just to adjust the date and time on the RTC module and also reading it. So yeah, I'll just go ahead and set that up. Yeah. So we'll be using I2C bus 1 and using dot peripheries I2C class, and then the DS1307 implementation that I did. Cool. Yeah, so it's basically just giving the I2C class the bus number and then the DS103 chip, the I2C instance, and then just disposing of it. Cool. And I've created a widget So Pieter can actually play around with the RTC module by adjusting it and reading the time from it. It's called RTC widget. So I'm just going to use that and give it the RTC that I've declared in the state. Cool, so let's see if we can get that to run. Cool, and then I'll hand over to Pieter to actually test it, make sure it works.
Okay, so let's try read. Okay, there we get a time. That seems to be incorrect. Maybe we can we change the date? What is the date today? Is it the 4th?
Yeah.
I think. Okay, here we go. Oh, that seems much better. The time?
3:30, roughly.
Something like that. Or maybe PM. Like. Okay, that looks somewhat better.
So yeah, maybe just unplug it and see if it.
To prove that it's actually we're reading it from the.
Yeah. And it's not just
okay,
some stored variable somewhere.
Let's pull the power. This is putting it. Okay. Oh, okay. Are we getting an error?
Yeah, I do see error transfer.
Okay, so there you have it, guys.
Cool. Yeah, so I guess back to Pieter.
I have to talk again now.
Yeah. That to the wrong side, no?
Okay, guys. So yeah, we have about 20 minutes left at the moment, and we're gonna quickly connect to the star navigator demo here. Yeah, so let's go ahead and do that. Actually, we have a CAN bus challenge now. We're gonna see if Hannes can manage to change the color on that. At the moment, it's the red power button. Maybe he can do a different color on that before the session ends.
Okay, so that one. Okay, so first I need to run it. Do you have a terminal open somewhere? Oh, wait. What's the name again? Space.
Just
I think you have to mirror the display.
I don't hear it. think you need to do?
I think we need to apply the same hack that we just did with the other device. Oh, close it. Thanks. Okay, so now it should run.
I think you might need to kill the other Flutter app running on there before the new one will
True.
launch.
That one.
Yep, it's dead.
Okay, let's see. It's copying over the app bundle. I think the Wi-Fi might be a bit slow. Oh no, it's this one, right? Yeah. Just wait a bit. How long did it take before? Ah, there it is. Ah, it's starting. Okay, so that's this starting.
It's a good question.
Yeah, it is.
We have a white screen with a black dot in the middle. Ah, there's something there.
Yeah, no. So that's I don't know. It's here.
Yeah. Okay. So yeah, now okay, let me try and change the wait. Okay. Wait. Wait, maybe show? Like take your hand out of the way. Oh, now it's red again. Now it's amber. Oh, and we can adjust the brightness as well.
Yeah, and this is talking via CAN bus to the board, which normally doesn't work with Flutter. There's an external package to make it work. It's called Linux CAN, and that's the package we use here. And the button pad that we use here actually doesn't speak normal CAN, but a layer on top of that, which is called CAN open. Yeah, it's a protocol above the real protocol, and yeah, maybe I can show a bit of about what we are actually sending to the device. So this is the CAN open driver that we use. So that implements CAN open for us. And here's just some basic stuff to reset the node, which is CAN open language for the button pad that we use here. And so this would reset the node. So it's like a special CAN frame we send to the device, and then it starts or resets. And this is how we actually open the CAN device. So we use Linux CAN here. It has a single instance, and we look for the right device or the right network interface actually. And if we found it, we need to check if the bitrate is correct. Otherwise, it won't be able to communicate because the button pad uses 125 bits per second. So super slow. It's like, I don't know, 20 kilobytes per second. But that's what people use in their cars. So, and yeah, and then we have this button pad driver, and that's what really implements the button pad. And so first of all, we start the node, set it to operational, and then to change the color of the button, we have this part here, which applies the LED colors. Yeah, it's just some bit magic. There's one bit for the red LEDs, one bit for the green LEDs, one bit for the blue LEDs. And yeah, then we put them together, and then we use PDO white, which sends a special formatted CAN frame. And that at the end results in the button pad driver, in the button pad to change the color of the thing. We can also blink it if we want to. Don't know if we showed that, but
Okay.
it would work.
How do we blink it?
There's a checkbox there for blinking. Yeah. Yeah, that also works. And that's just to showcase that we can interface these, first of all, that we can use these industry buses in an actual embedded device. That's really useful. And yeah, actually talk to hardware in that way. So, yeah.
It's quite fun. Now it's going all the colors.
Yeah. You could also talk to an engine control unit if you want to, using CAN bus, because they use CAN in their cars. So yeah. Any other challenges?
No, I think that's it for today. How much time do we have left?
10.
Okay.
10 minutes.
10. Guys, I guess we can now have a bit of a FAQ. So if any of you have questions, maybe raise your hand.